Well, so now you show my my slides.
Yes.
Is that right? Or
Yeah.
yes. Okay. Thank you very much for the invitation, and thank you, Paul, for all your organization in this project Ecodep with your collaborators. So it has been a very nice talks, and I'm going to talk about epidemiology as well, but not COVID-19. We will talk about a disease which is hepatitis C. So this is a work that I did with my PhD student, Viet, and also with collaborators. So Marie-Geoffrey Roustide, who is a sociologist. Jean-Stéphane Dersin, maybe you heard about him because he was in charge for the CNRS of the mathematical committee for the COVID-19. Yazdan Pana, who was in the Conseil Scientifique, so you also probably saw him a lot. And Cyrielle Dumont, who is a maître de conférence in Lille 3, and Anthony Cousien, who is a former student of mine, and presently he's a postdoc in CERN. So let's start with the motivations. So hepatitis C virus in France has a very low global prevalence. It means that probably none of you have hepatitis C. But if you look in the special populations of people having who inject drugs, it's very high. It's almost 60%, and that's why it is a concern for sociologists and doctors, not for global public health, but at least to control in these populations the level of the epidemics. So a few years ago, in 2012 and 14, it appeared the new treatment, which was very efficient with very side effects. And thus, there was a new question, which was to give the treatment preventively, to use the treatment as prevention in order to prevent people from getting hepatitis C virus. And at first, the doctors were really asking, also wondering whether it would be possible to completely eradicate the disease. But now we know it's not the case, unfortunately. And as always, when you have to deal with public health policies, of course, you need some models or facts that tells you that the treatment is effective, but you are also very aware of the cost. For instance, you will not give the treatment as prevention if it is not efficient given the cost that it will have. So that's why Anthony Cousien, during his PhD thesis, he did a model with 3 levels. So the level that people know most commonly is the second one, so the one in the middle. The second one is a usual compartmental models, and it describes the history of the patients in the public health system. So you have S, who are the susceptible or healthy patients, and then they can be contaminated and be first asymptomatic. That's the A, and then there are several phases during which they are in contact or not with the public health system. And that's the middle of the model. Then you have the right of the model, the number 3, who describes, in fact, what am I doing? Which describes, in fact, I think I can write on so we are now here. It describes the history of the disease inside the patient. So F01 is the first state of the disease when you are not reinfected. And then the disease progresses. And the problem of hepatitis C is that it's not so problematic if it's in the first phases, but it can end with some very important liver disease, and you can even need a transplantation, for instance. And this was important to model because when you say, for instance, that you give treatment as prevention, or when you say that you give treatment only at certain stages of the disease, you need in your mathematical models to have this information that is also represented. And in fact, today I will focus on the first part of the model, this one, which is the social network of the people who inject drugs, because hepatitis C virus is transmitted from people to other when especially they share injecting materials. So they can be also other reasons, for instance, sexual intercourse, but mostly it is because they share injecting materials. And even when the drug users don't use the same syringes, for instance, they can share some other materials for which they are not completely aware that it's dangerous for them to share them, and they can still transmit the disease when injecting together. So this, all these things are detailed in the paper by Anthony, which I mentioned here. And of course, you can imagine that the outcome of your model depends very strongly on the parameters, of course, but this is it's somehow very well documented, but also on the knowledge of this social network. If you don't take the true social network, or if you change in your model the social network, you can see by simulations that you can obtain very different outcomes. And we worked on the robustness of the model given the social network that we assumed at the beginning. But of course, it is of great interest to have some insight of the network. And that's why we moved from these very applied situations to a very more theoretical question, which is how can we do statistics on network, and how can we discover hidden networks? So of course, another difficulty in our problem is that drug use is illegal in France. So you cannot just put in some database the name of all your drug users and ask them if they have, if they inject together or not. All the database have to remain anonymous, and there's a lot of issues on privacy, and some of these issues we heard when in the COVID situations, when dealing with, for instance, different applications that allows you to trace back COVID in contact tracing. So let us talk about the respondent-driven sampling, which is the methodology that we developed to infer the social network. This work was done much before the COVID-19 outbreak, but of course you can transpose some of the idea mathematically to model contact tracing, although I think that contact tracing is much more difficult than what I will present today. So when an individual I is interviewed, so you interview individuals and you ask them about the people with whom she or he injects. And the idea is that, for instance, the drug user mentions to you 10 of his contacts during the 3 last months or during the 6 last months. It can depend on time also. And then at the end of the interview, you give her or him some coupons. So the number of coupons is small c, but you can think of 3 coupons, and with the idea that she or he will distribute the coupons to some of the partners. So either you let the interviewee distribute the coupons at random, or you can try to propose to her or him the possible partners to whom the coupons should be given. For instance, during the interview, the drug user described really the relation that he or she have to their different partners, and you can say to him, it would be good that maybe you give a coupon to this individual if you think that he or she would accept to come and take the interview. So the people who obtain the coupon can come themselves to take the interview, and then we give to them coupon as well, and it goes on like this. So this recruitment is also known in some literature as related to the snowball sampling. to be enticing, the people who take the interview and the people who return the coupon become some they can be given some financial compensation, but it's for drug user in our study it's very small. It's like ticket restaurants or things like this. I hope it was clear for the presentation of the method. So what happens when we have interviews and people return their coupons? So we have a database where we can ask some information. For instance, you are not able to ask for the full name, but you can ask for nicknames, for instance, and you can also ask for description of the people. For instance, if the people was tall with red hair and some specific tattoos, for instance, this can be written in the database. And you also record the coupons. So the coupons give you ages between vertices of your social networks. And then the description can allow you to find other hidden edges. For instance, if two individuals describe contacts with the same individual with the same characteristic tattoo, for instance, you can guess that there are edges between them and this third individual, even if you have not interviewed the third individual, and even if you're not completely sure of it. So all this literature on the respondent-driven sampling has been, so it was a method that has been introduced by Hackathon in 1977. And then there was a big piece of literature by Krista Gilley and her co-authors. But from a statistical and applied statistical point of view, many things have been done, but there's still a lack of theoretical results on RDS. So that's why I propose this subject to Thuy, my current PhD student, and we hope to build some pieces of exploration in the literature. So let me check time. Okay. So we were not the first one who did RDS in practice. So we were very much inspired by a study by Australian data. So the reference is given here. It's David Rawls and co-authors. And they obtained, for instance, the left data. And in fact, we finished now our RDS sampling, and our data is the right graph, which is not completely finished because we still have some data to exploit, but the graph is almost like this. Okay. So in fact, you can already see from the qualitative point of view that both graphs have different characteristics. For instance, one striking thing of the Australian graph is that it is a planar graph, which I think is by chance. It's almost planar. Of course, you can say maybe at this point you have some crossings, but it's almost planar, whereas the French graph shows much more complex motifs. And we have also more individuals than the Australian data because we managed to carry a longer study as them. So this difference between the networks can explain also some differences between the products and the ways that people inject drugs in these different countries. And these are things that we aim to explore more in the future. So today, in fact, the question that I will ask is a more simple question, is that, for instance, in Paris, we obtain these data here, and we can ask a very natural question, that is whether these data are really representative or not of the social network in Paris. So do we have guarantees that when we run our RDS and interviewed drug users, do we have guarantees that we observe a network that is almost a good one to put in our model as an input? Okay, so this is just a zoom on the component that I plotted here to show that it was more complicated. And also that there were other questions by sociologists which were, for instance, how many coupons should we distribute, and can we predict the outcome of the RDS before running it. And what we did is that we tried to model the exploration process and started at first with very schematic very schematic cases that are a bit far from the reality, but then you will see that we try to get more and more close to what happens on the field. So what is, if we try to put equations on all the things that I described, how does it work? So we have an exploration graph that we can consider as a discrete time process, where the time corresponds to the number of interviews that you have done. So for instance, you have a situation after the first interview, after the second interview, etc. And at each time, you can describe your whole population. So assume that we are in a closed population, so no entrance or death of drug users, for instance. So the total population will be of size capital N. And after the small nth interview, you have a certain number of coupons that you have distributed. So it is not necessarily C times N, because if somebody has only one contact, you can give only one coupon. But you have a certain number AN of coupons that have been distributed but not returned yet. So AN is all the possible number of, it is the number of people that you can still interview. And of course, when AN is equal to 0, it means that either you are respondent-driven sampling stop, either you have to initiate a new tree by giving new coupon to a new chosen individual. And then you also have individuals, BN, who are the individuals who have been mentioned, but not given any coupons. For instance, if the first individual mentions to you 10 contacts and you give him 3 coupons, you have 7 people who are in your database in some sort, because they have been described a bit. You have some description of these individuals, but they don't have coupon, and unless they become a coupon by other interviewees, you will not interview them. And the rest of the population, so is the number of unexplored vertices. It is the size of the population, capital N, minus people already interviewed, small n, people with coupon but not interviewed, and people mentioned but without coupon. One difficulty in our case is that in fact, we don't observe capital N. One of the questions is how many drug users are there. If there are a lot of drug users, it's not the same as if there's a small number of drug users and you observe them all, because then you can do different public health policies. Okay, so capital N is unknown, and we observe, in fact, AN and BN. So this is the process XN. And we can try to describe the transitions, how AN and BN evolves, and I will try to discuss it in the next slide. So what happens when you interview a new individuals? So the number of coupons, AN, first it decreases by 1, because one individual brings the coupon back to take the interview. But this individual has a certain number of contacts, and you will give to this new individual coupons, so that there are new individuals with coupon. So if this individual has Y coupon, YN plus 1 coupon, you give to him C coupon if it's possible. For instance, if Y is equal to 4, so AN will increase again by 3. But if this new individual has only 1 contact, of course, you can give to this individual only 1 coupon. So the increase of AN is YN plus 1 infimum C. What about the number of individuals who are mentioned but without contact? So it was the number of individuals mentioned but without coupon at time N. To this, you add HN plus 1, who is a new number of neighbors mentioned by the N plus 1 interviewee, but who were not mentioned before. Okay, and of course, some of them have coupons, so you have to subtract the number of coupons that you give to the individual. If you give to the individual n+1 3 coupons, so you do -3. If you give to the individual n+1 2 coupons, so you do only -2. Okay. So what you see is that the transitions of the processes A and B, they depend very much on the assumptions that you have on the graph, because they depend on the distribution of these three other random variables: the number of neighbors not interviewed and without coupons, the number of neighbors not mentioned before, and the numbers of neighbors who were already mentioned but without coupons. Okay, so let us look what happens for very simple cases. So I have not said before, but social network is considered as a random graph. The random graph in the sequel, we will sometimes use the adjacency matrix. So it is a matrix indexed by the pairs of vertices, and GUV is equal to 1 when you have an edge between U and V. So if you look at Erdős-Rényi graph, which is a very simple example of random graphs, it is a random graph where you drop an edge, you put an edge at random between U and V, independently of all the other pair of vertices, and you do that with a probability P. Okay, so GUVs, these random variables, are all Bernoulli independently identically distributed random variables with Bernoulli distribution. You can try to put some structure in your graph. So if you want something more clustered or something like bipartite graph, for instance, you can use something which is which is developing at the moment. There's a lot of literature about that, which are the stochastic block models. So stochastic block models, you can think of them as generalizations of Erdős-Rényi graphs, where each vertices are given some colors, or so you have a class for every vertices, for every vertex, and assume here that we have Q colors. Okay, so you paint your vertices with Q colors, and the probability that the vertex U is linked to the vertex V is independent of the edges between all the other pair of vertices, but it depends on their respective colors. So you have probabilities, and the probability that U and V are linked by an edge is P ZU ZV, where ZU is the color of U and ZV is the color of V. Okay, so for instance, here you will have pi 1 1, pi 1 2, pi 1 Q, and etc. and until pi QQ. Okay, and here it's a mistake of me. The proportions of each color are called alpha in the sequel. So this is something which is much used, but of course you can also think of other models. For instance, if you look at the literature on the Facebook graph, for instance, people like to describe the graph by the degree of the individuals, and especially the degree distribution, which tells you what is the proportion of individual which given degrees. And another model which conveniently satisfies the degree distribution are the configuration model, where you give a degree distribution and you construct by pairing vertices accordingly a new graph. Okay, but today I will focus really on these two types of graphs, the Erdős-Rényi graph and a generalization of it, which is the stochastic block model. So I have to speed up a bit. So when you have Erdős-Rényi graph, for instance, you can derive the exact distribution for all the random variables y, h, and k that describe the transition of the process x. And the process x, in this case, is a Markov chain. So you can solve a lot of problems with a potential theory. For instance, you can predict the issue when you will have no coupon anymore, how many people you will have interviewed at this time, etc. And you can program these equations numerically. So I don't really want to enter into the details. I just mentioned that one of the first work of Tran in her PhD thesis was to look at what happens if you have large graphs. So she did that for Erdős-Rényi and for stochastic block models. And she can have a profile of the number of people that you explore in each colors with the RDS when you proceed like this. Okay. But now we can ask another question, which is what happens about the topology of the graph which is discovered. Okay, the first result of Tran, which is shown in this graph, it shows given time. Time is here, I record the number of interviews. What are the proportion of the population explored? And you can see that in the end, when you arrive here, the total number of interviews that you will have done when you don't have coupons anymore corresponds of the abscissa at which you hit 0. Okay. And so you can have an idea of what is the proportion, and this is a time here is rescaled between 0 and 1. So it can give you an idea of the proportion of the graph that you will have explored. And what we see is that when we have a sparse graph, in the sense that the degree of individual and the number of edges is small according to n square, the number of possible pair, then you can see that we can find conditions, at least numerically, so that a very large proportion of the graph is explored. So we can now wonder what happens when we have large graph. So when we have large graph, in fact, the discrete model and exact model is very complicated. So one thing that we do when we are probabilists is that we can look for continuous approximation, or at least some approximations that becomes more tractable. So for instance, when you have complicated random walks, sometimes it's convenient to look for diffusion approximation of these random walks. So this is exactly what we do. And what we say is that we look at very dense and large graphs, and one approximation of them is what we call graphon. So graphon is a function from 0,1 square to 0,1, so you can represent it like this. And in fact, it is a generalization of adjacency matrix. So adjacency matrix, you can always represent them graphically by saying that if your individual 1 is related to individual 2, you will put a dot at this point, okay? Instead of putting 0 or 1s, you do a picture where you put a dot at this point, and you can do that a bit differently. What you can say is that, for instance, instead of putting individuals at the intersections, so to have labels, you can put individuals in the columns, and instead of dots, you can color the square corresponding to the individual 1 and the individual 2. And if you think of this kind of thing, so you have some colored square, and your graph becomes larger and larger, so the square becomes smaller and smaller. In the end, what you see is not the reunion of all the white and black squares, but you see some gray level. So this is the graphon. Instead of seeing something which is either black or white, you see a gray level, and this is a kappa. If kappa is equal to 0, you can assume it's white. If kappa is equal to 1, it's black. And else, it tells you what is the intensity of connections between 2 points. So if you have a gray level, and you look at x here and y here, and you wonder what is the probability that an individual in this region x is connected to an individual in this region y, it will be kappa of xy. Okay. Instead of putting things which are really black or white and saying there's an edge or there's not an edge, in the limit, when you have dense graphs, you say what is the probability of connection between some neighborhood of x and some neighborhood of y, and it is given by the function kappa. So this first point was to explain that graphons are a generalization of graph, because if you have a graph, you have a natural graphon behind it. And to have to fix idea, if you have an Erdős-Rényi graph, the connection intensity is homogeneous because Erdős-Rényi, you put two vertices at random, whatever they are, the probability of connection between them is P. So the graphon corresponding to Erdős-Rényi graphs, dense Erdős-Rényi graph is something constant equals to P. And when you have a stochastic block model, what happens is that you have your different colors. So for instance, here, color 0 and color 1, or sorry, color 1 and color 2. And the value of the graphon on each of these regions corresponds to the probability of connection between these types, 1 and 1. So it is P11, and 1 and 2, it's P12 or P22. So I hope it was clear. Now I try to explain what is our idea. So our idea is to try to have a graph or graphon associated to the RDS, to the exploration of the random graph, and we will compute the distance between the true graphon of the graph, the true graphon, and the estimated graphon. And of course, we hope that it will converge, but in fact, this is not always the case. So to compute the distance between two graphons, we need some metric. So maybe I can skip this a bit. What I want just to emphasize is that this metric is really, it is a generalization of topologies that you can put on measure space to measurize the space of measures. So let me say just one word about it. So you can take small motifs that you call F. F is a small motif. And what you will do is that you will count the number of motif F in G. So this is this quantity. It's renormalized, so I don't want to go too much into the details, but you count the number of motif F in your graph G. Of course, you can count the motif F that you have in your graphon as well. So this is not an exact count because the graphon is a continuous object, but what you see is that this corresponds to the probability to have the motif F, the small graph F, between the vertices xi, xj, etc. And then you integrate over all the vertices and it gives you some intensity of the motif F in your graphon. And what you do is that you compare the proportion of motif F in G and the proportion of motif F in K in the graphon kappa, and you sum that over all the possible motifs. And motifs are finite graphs, so you can find some enumeration of this, and it defines to you a distance between the graph and the graphon. And one very important result was obtained by Atreya and Rollin. So I put the reference, but in some other slide. So I'm sorry, it's not here, but in another slide. Oh, sorry, it's because I don't read my slide properly. Before explaining, so what is the exploration, the RDS on the graphon? So here I present a very easy case where we take just one coupon. So here it's just one random walk on the graphon. If you take C greater than 1, you have a branching process on the graphon, but I don't want to enter into the details today. It is a work in progress currently. So when you walk on the graphon, of course, the transition of the random walk that corresponds to the RDS, and it tells you who gets interviewed after your current interviewee. It depends of the connections. If your interviewee is connected only to individuals, for instance, of color 1, you are sure that the individual that you will interview at the next step will be of color 1. So we can compute the transition of the random walk, and you see the transition of the random walk when the current individual is at the state x in 0, 1. It's given by kappa xy, which gives you the intensity of connection between x and y, and you have to renormalize it, of course, so that it becomes a probability transition. Under some assumptions which are quite classical, this Markov chain admits a unique invariant probability measures that we will call M, and this stationary measure is very important. So this stationary measure is N, and if I go a bit fast, the cumulative distribution function of this stationary measure will be called gamma. So let me skip this, because I see that my time is going a bit forward. The main result by Athrea and Rollin, which is for me a very important result in this problem, is that if you look at the graph generated by the random walk, so you have the graph of who obtains coupon from whom, and because you have some description of the vertices, you are able to construct some edges between the individuals that you have interviewed, because you have some knowledge of them. And the distance between the graph that you observe by your graphon, by your random walk on the graphon, and the graphon, it does not converge to zero, but it converges to zero if you distort your graphon. So gamma kappa is a distortion of the graphon, which is defined, I forget where. I'm sorry, I'm navigating between my slides. Well, I don't find again the description, but it is a graphon which corresponds to gamma of x and gamma of y. Okay, and the idea is that if you interview individual in the population 1, for instance, and if pi11 is very high, it means that you have a lot of connections between these individuals. You will stay, your random walk will stay a lot of time in this class before going, for instance, to the class 2 and then moving inside the class 2. And you will have the impression on the graph that you have explored that the class 1 is very big, but in fact it is not that big. You have to correct it by the cumulative distribution function gamma of the random walk. Okay, so now there are, and I will end up with this. There are several strategies for estimating and debiasing the network that you have found. Either you do, for instance, likelihood methods, but one difficulty is that you see that if you suppose that the colors and the proportion of colors is known, is observed, that if you suppose that you observe the colors of the individual that you observe, even in this case, which is already very optimistic, you will see that you can express all the parameters pi and alpha with respect to some parameters. That is a zero of this function that we have here. So you see that this function already has a lot of zeros. So you have to select the good zeros. And already in the best case as possible, it's complicated. So assume that you have found some good algorithms that allow you to find the good parameters in case you observe the types of the individuals. Then when you don't observe the types, you have to use some SAEM method or other method that allows you to reconstruct the types of the individual and then to obtain the parameters that you have. So this is possible to do, but you can have also another estimator based on the bias that is explicitly obtained by Athrea and Rollin. The idea is to do as if your observations were not biased. So you can define the estimator that would be the estimator in the case where you don't have any bias. And then you can try to estimate the cumulative density function of your random walk. And once you have this, you can debias quite easily the estimator that you have. And of course, in this case, you can proceed if you observe the types of the individual, or if you don't observe them. And in this case, you can use a expectation maximization algorithm, which is quite classical. So I don't detail it here. And I just would like to show some results. So we did these results in a very particular case where we have only two colors, 1 and 2. So already it was also to check that everything can go all right. And we did in each time two block of simulations. Everything is coupled so that the simulations used are always the same. So everything is comparable in the simulations. And we did the maximum likelihood. That was a bit tricky, as you saw. And then SAEM is the maximum likelihood, but we reconstruct the type of the individual, assuming that the types are unobserved. And then we do the estimation with the graphon, assuming the type is observed, and the estimation with the graphon, estimating that the type is not observed. And what we see is that the true values for the different parameters, so this is in the order alpha 1, so the proportion of individual of type 1, and then the intensity of the connection, pi 1, 1, pi 1, 2, and pi 2, 2. Okay, so the true values are in red. It's a vertical line in red, so you can see it works quite well. And of course, if you do maximum likelihood, in some cases it works well. For instance, for the pi, but for the alpha, it's the variance is of the estimator is a bit large. And what is very difficult to do is maximum likelihood plus SAEM. So in case you don't observe the types of the individual, in fact, the strategy which consists to do the graphon as if you had non-biased observations, and then estimate the cumulative distribution function gamma and debias it, seems to be better. Okay, so I thank you very much. I think I am out of time, and of course, if you have questions, I will be happy to answer to them.
Thank you very much. I don't see questions directly in the chat, but I'm sure people have some questions. Any questions? Again, you can say in the chat that you want to ask one. Anyone? Yes. I see. Anyone? Question?
Well, I'm sorry if it was not clear.
Okay, I don't know if people are hungry. It's not time yet, though, to be hungry.
Okay, well, so maybe we can else thank all the organizers of the conference. There's maybe a round table, and Paul wants to say something about it.
Yeah.
Thank you very much for this very nice talk indeed. So we now finish the session, I guess. What about meeting again at 3 p.m. Paris time? Okay, for a round table. So